Sometimes you want to determine the amount of a compound which is not ionic and is rather covalent and doesn't lend itself easily to precipitation by another ion. When this is the case, we can use combustion analysis to determine the amount of the compound and the amount of the different types of atoms in that compound. If you haven't already watched the video on gravimetry, you should do that before you watch this video, because this type of analysis, combustion, is another example of a gravimetric analysis, or analysis by mass. As with all types of chemical analysis, combustion analysis relies on a known reaction. In this case, the known reaction is the combustion, or the combination of the compound with oxygen to burn the compound and to form oxides of the particular elements that make up the compound. Most often this is done with organic compounds that contain carbon, some amount of carbon, some amount of hydrogen, and perhaps some amount of oxygen. When we combine these compounds with oxygen, excess oxygen, we form the oxides of the elements, so carbon dioxide, water, which is the oxide of oxygen, and we can take the mass of the amounts of CO2 and H2O that are produced and use those to back calculate the amount of carbon and the amount of hydrogen in the compound. Let's see how this works by doing the following problem. If we start with 0.0956 grams of a compound that contains carbon, hydrogen, and oxygen, and we completely burn it or combust it to form CO2 and water, and we measure the mass of the CO2 and the water that we produce, we want to know what are the mass percentages of carbon, hydrogen, and oxygen in the original compound. So we can start with the carbon and the hydrogen, and we know that all of the carbon from the original compound, so if the original compound contained X amount of carbon relative to Y amount of oxygen relative to Y amount of hydrogen relative to Z amount of oxygen, and we burn it in enough oxygen to completely combust it, we will form X CO2s, because every carbon from here is going to combine with two oxygens to form a CO2. So we get one CO2 for every carbon. That balances this reaction. And we know that we are going to make Y divided by 2 H2O, because every hydrogen, we need two hydrogens to combine with one oxygen. And so if we have two hydrogens over here, Y divided by 2 times 2 gives me the Y hydrogens that I had over here. The oxygen that is in this compound just becomes excess oxygen in the system, and since I've already added an unknown amount of oxygen, I won't be able to determine the amount of oxygen by mass, but if I know the amount of carbon and the amount of hydrogen, I can figure out the amount of oxygen by difference, because I know the total mass of the compound that I started with. So if we collect our information, we know that we have 0.0956 grams of this, and we produced 0.269 grams of the CO2 and 0.110 grams of the water. So now we can do like we usually do when we're doing any stoichiometric problem, and we can use the mass of our products to determine how many moles of each of these products we have produced. If we know the number of moles of products that we produced, then we know the number of moles of carbon and the number of moles of hydrogen, because each one of these contains one carbon and each one of these contains two hydrogens. That allows us to find the number of moles of carbon relative to the number of moles of hydrogen in the original compound. So the CO2 has a molar mass of 44.01 grams per mole, and water has a molar mass of 18.015 grams per mole. And so I can use the mass and the molar mass to find the number of moles. So I take the mass and I divide by the molar mass, and I find the number of moles of CO2 in that way. So 0.269 divided by 44.01 is equal to 0.00611 moles of CO2. Likewise, I can do the same thing for the water, and 0.110 divided by 18.015 is equal to 0.00611 moles of water. Now, I don't want the number of moles of water or the number of moles of CO2. I want the moles of carbon and the moles of hydrogen. And so each CO2 contains one carbon, and so I will have the same number of moles of carbon as I did CO2. So I have 0.0061 moles of carbon. However, we can see that for water, every water contains 2 hydrogens. So I'm going to have twice as many hydrogens as the number of moles of water. And so to get the number of moles of hydrogen, I have to multiply this by 2, and I will have 0.0122 moles of hydrogen. To find the mass percent of carbon and hydrogen in this compound, I need to know the number of grams of carbon and the number of grams of hydrogen. So to go from moles to grams, I just need to multiply by the molar mass. And so for carbon, the molar mass is 12.011 grams per mole. And for hydrogen, it is 1.008 grams per mole. And so if I multiply 0.00611 times 12.011, I end up with 0.0734 grams of carbon. And if I multiply 0.0122 times 1.008, I end up with 0.0123 grams of hydrogen. And then mass percent is going to be the mass of the part of the thing, so the mass of the carbon in this case, if I want mass percent carbon, divided by the mass of the whole thing, and the amount of the total compound was 0.0956 grams that I started with, and then of course times 100% to get it into percentages. So 0.0734 divide 0.0956 times 100% is 76.8% carbon, and then percent hydrogen will be the mass of hydrogen divided by the mass of the whole compound times 100%, of course, and we end up with 12.9% hydrogen. So we know the percent hydrogen and we know the percent carbon, and what we notice is that these two things do not add up to 100%. In fact, they add up to 76.8 plus 12.9. They add up to 89.7%. So I am missing 100 minus 89.7 is equal to 0.0956. 10.3%. So what's missing must be the oxygen that was in this compound, which I can't get from the masses of this because some of the oxygen over here is from oxygen that I actually deliberately added to the sample. And so the amount of oxygen that was actually in the sample, I have to get from difference. And so I can say that I have 10.3% oxygen in this sample. And that way I can get the percentage carbon, the percentage hydrogen, and by difference, the percentage oxygen in my original compound.